Hello everyone. Here we're going to be talking about opportunity costs, feasible frontiers, and comparative advantage. Now, when you think about comparative advantage, you've probably heard about this idea before when you've spoken about, say, trade between countries. But we're going to be talking about it between two different people who could be engaged in exchange. Now, that example of two people, or the metaphor of two people, can be transferred upwards to two countries. But it also is helpful to think about this at an individual level. So let's think about this. We're going to consider two people, April and Brett, and they have two tasks that they can engage in, either data entry or graph making. So they're both engaged in some kind of IT or kind of data type task, and they can engage in data entry or graph making. Now, with absolute advantage, what do we mean there? Absolute advantage is when a person or nation has an absolute advantage in the production of a particular good if, for a given set of available inputs, they can produce more of it than another person or country. Now, that condition in italics here, for a given set of feasible of inputs, they can produce more of some output than another person or country. So when we're thinking about that, what that could mean is that your available input could be an hour of time, it could be some set of inputs like land, it could be some capital, it could be labor, these kinds of things. Those are the inputs and your use of those inputs going into the potential output you could produce. Now, comparative advantage is when is for a person or nation. They have a comparative advantage in the production of a particular good if the opportunity cost to them of producing it is lower than it is for another person or country. Okay, so notice the previous one said with given feasible inputs, more can be produced. Here with comparative advantage, we're talking about having the lower opportunity cost. Okay, so those are just the definitions of the terms, but now we're going to look at an example between April and Brett to try and get a sense of how this looks. So here we have two feasible frontiers, one for April and one for Brett. When we think about these feasible frontiers, what we're going to see is that we've got two potential outputs that they can engage in producing. The first one is data entered along the x-axis. The second one is graphs made along the vertical axis. What we can see here is that the intercepts for April are 20 and 11 respectively, and the intercepts for Brett are 8 and 10 respectively. Now, there's another condition here that you can see from this line from the origin, and that's that each graph needs 1,250 keystrokes to be produced. You need data in order to make graphs. That's going to come in later when we need to talk about exchange between April and Brett, and if one of them engaged in one task and the other one engaged in a different task. And the other thing is that even if you're doing this by yourself, you have to think, I need to enter data in order to make graphs. Okay, so that's what that little orange line is there for. Now, we have a question. Looking at this graph, who has absolute advantage? Also, looking at this graph, who has comparative advantage? And then, importantly, why? So take a moment for yourself. Think, can I identify from this figure which of them has absolute advantage? Can I identify who has comparative advantage? Can I also explain why it's the case? Now, if you're a little unsure of the why, don't worry. That's what this video is for. We'll go into unpacking why in a second. Okay, I'm going to assume you took a moment, you tried to answer those questions, you took a moment to pause and had a go, and I'm going to now think about how we'd answer those questions. So, here we go. April has absolute advantage in the production of both goods because her feasible frontier is outside of Brett's. So, with the same amount of time available to her, April is able to produce 20 graphs, or she can produce 11,000 strokes of data. Okay, so she's got 11,000 keystrokes of data. So she can produce both things. In producing both things, she produces more of them with an hour of time than Brett does. So she has an absolute advantage in the production of both goods. Okay. Now, Brett has a comparative advantage in data entry because his feasible frontier is flatter. What this means is that he has a lower opportunity cost of data entry in terms of graphs that he gives up in order to enter data. So even though April has the comparative advantage in the production of both goods, Brett can still specialize in one of the productions of goods because he has a lower opportunity cost for producing data than for producing graphs. Now, what we'll also see is that April has the lower opportunity cost of producing graphs than data. We'll explain exactly how we get to that step by step as we proceed in this video. But think for the moment, what are we trying to do? We're going to identify the opportunity costs for the two of them of their respective components. So to do that, we're going to use this table. So this table is summarizing some data that we have in the figure, and then we're also going to unpack how we get to the opportunity costs in a moment with some mathematics. But the first thing we want to see is we had each of their intercepts in our from our graphs. And what we can see there is that when we have maximum possible data entry in terms of thousands of keystrokes, Brett could enter 10,000 keystrokes in 1 hour, and he could make 8 graphs in 1 hour. For April, she could enter 11,000 keystrokes of data in an hour, and she could produce 20 graphs in 1 hour. Now, what we can see is that the numbers for April are greater than they are for Brett in both circumstances. Therefore, April has absolute advantage in the production of those goods. Now, we then have these numbers over here, and these are the opportunity costs. And we can see there that Brett has an opportunity cost of 0.8 in terms of data entry versus 1.82 for April. And so what is that saying? It's saying that April has to give up 1.82 graphs in order to produce 1,000 keystrokes of data, whereas Brett has to give up 0.8 graphs in order to produce 1,000 keystrokes of data. We're going to show you how to get those numbers in a moment. But what I want you to think about this as is, what do I have to do? I have to sacrifice some of one unit in order to get more of another unit. So I'm sacrificing some graphs in order to get more data, or I'm sacrificing some data in order to get more graphs. So we've just looked at that first line over here in terms of who has the lower opportunity cost of data production. But what we can also see is that we have the converse. We have April having a lower opportunity cost for producing graphs versus Brett. So for graphs, April has to give up 0.55 units of data input, whereas Brett has to give up 1.25 units of data input. So as a result, April has the lower opportunity cost for producing graphs. When she has a lower opportunity cost of producing graphs, she has a comparative advantage in graph production. Okay, now, to unpack this idea of the opportunity costs, what we're going to do is we're going to see that we've got some different notation here. So the first thing is we're going to talk about the fraction of time that is required in order to produce either one of the units. So for the X good, we can see that April requires 1/11th of 1 hour to produce 1,000 keystrokes. Remember, on our x-axis, 1,000 keystrokes is 1 unit of x. So she produces 11,000 keystrokes in an hour. Therefore, what she can do there is the fraction of an hour required to produce 1,000 keystrokes is 1/11th. So 1/11th of an hour to produce 1,000 keystrokes, or 1 unit of x. For Brett, that's 1/10th of an hour. He requires 1/10th of an hour to produce 1 unit of x. So we can see that there in terms of 1/11th and 1/10th. Now, how do we get those numbers? We saw here for Brett, he can produce 10,000 keystrokes in an hour. Therefore, it requires 1/10th of an hour in order for him to produce 1 unit of x. For April, she can produce 11. Therefore, she requires 1/11th of an hour to produce 1 unit of x. Now, we also have our other ones over here, 20 and 8. And so what we can see there then is what each of them requires in order to produce one graph. So for April, she requires 1/20th of an hour to produce one graph. For Brett, he requires 1/8th of an hour to produce one graph. And so that would correspond to our A, Y. And we can see those exact numbers here. So X is the thousands of keystrokes of data entered, and Y is the number of total graphs made, as I've already said. And then T, capital T, is the total time, 1 hour. So when thinking about this, what can we see? We can see that the amount of time multiplied by the output, and again, the amount of time required multiplied by one output of Y, those multiplied by each other has to be less than or equal to the total time allocated, where capital T is 1 hour in this case. So what we want to think about there is for each of them, we have the fraction of the hour required to produce 1 unit of X and the fraction of hour to produce 1 unit of Y, multiplied by the corresponding numbers of graphs made or data entered. When we have those, the total amount of time spent on those has to be less than or equal to 1 hour. That's what this is saying. Now, what you can see here is that this looks very similar to a budget constraint. Remember what we had previously for a budget constraint is that we saw the price of X times X plus the price of Y times Y must be less than or equal to your total available budget. Okay, so your total available budget was equal to M. So if that's familiar, it's the same kind of idea. You have a time budget that you're allocating to two different tasks. Okay, now, how do we think about the opportunity cost? We want to rearrange the condition we had on the previous slide in order to find an equation y as a function of x with the parameters on the other side. And that's exactly what we do here. So what do we want? We want to have y on our left-hand side. So what are we going to do? We have a y times y equal to t minus a x x. Then what do we have to do? We have to divide through by ay. If we divide through by ay, we get the equation as shown here. Y equals capital T divided by ay minus ax over ay times x. Okay. Now, what you should remember here, similar to what we had with the budget constraint previously, is that the negative of the slope of the budget constraint, or the negative of the slope of your time constraint, is going to be equal to our marginal rate of transformation. So what we have to do here to find the marginal rate of transformation equal to minus dy dx, we find minus dy dx of that equation, and that will give us the opportunity cost of producing x in terms of y. And what we can see that is, if we differentiate this function with respect to x, we're going to be left with minus ax over ay. Okay? But then we want to make sure that we have the minus sign in front of that, and so a minus times a minus is a plus, therefore we are left with ax over ay. That is our marginal rate of transformation, or our opportunity cost of producing an additional unit of x in terms of how much y we have to forego to produce it. Okay, so now having found that number, what can we do? We had ax and ay for both of April and Brett. We can substitute those numbers in to find the marginal rate of transformation, or the opportunity cost for each of them. So let's look at that now. So using that equation, and just a reminder, we said that MRT equals AX over AY, and that is our opportunity cost. All right, so for doing that for April, we can substitute in AX over AY. For April, her AX was equal to 1 over 11. Her AY was equal to 1 over 20. So what is that? That's 20 over 11, and that is 1.82. So her marginal rate of transformation is 1.82. For Brett, on the other hand, it was 1 over 10 divided by 1 over 8. That gives us 8 over 10, which is equal to 0.8. Because 0.8 is less than 1.82, Brett's comparative advantage is in data entry. He has the lower opportunity cost of producing data entry X in terms of graphs Y foregone. Okay, so he has to give up fewer graphs in order to enter 1,000 units of data. Now, that's all well and good. We found the slope of these functions, and so therefore we can think about the marginal rate of transformation. But now we have to go in the opposite direction. And when we go in the opposite direction, we're trying to think of who has to give up less x in order to get an additional unit of y. And when we have to see that, we basically have to look at the inverse of the number that we just found. So April, for her, we're going to have to invert her marginal rate of transformation and basically just find 1 divided by 1.82. And we see then for her opportunity cost of producing units of y in terms of how much x she has to forego is 0.55. For Brett, on the other hand, he has to give up 1 divided by 0.8 equal to 1.25. What does that mean? He has to give up 1,250 keystrokes in order to produce one graph. For April, what did she have to give up? She had to give up 550 keystrokes in order to produce one graph. Now, because 0.55 is less than 1.25, April's comparative advantage is in making graphs. She has a lower opportunity cost for making graphs Y in terms of data entry X that she forgoes. Now, if you want to just quickly skip back to the figure, which we're going to do over here, we can also think about this in terms of these curves, right? So we can see that for April, if we're just looking at the slope of her line here, the slope of this line is equal to minus 1.82, right? Because remember, that was equal to dy dx. Okay, similarly for Brett, what did we have? His dy dx was equal to 0.8. He had the flatter slope. Because he had the flatter slope, that means he gives up less y in order to produce a unit of x. Okay, now we also have to remember though that opportunity cost doesn't only go in one direction. It doesn't only go in the direction of how much y do you give up in order to get a unit of x. So how much y you give up in order to get a unit of x. We also have to interpret it in terms of how much x you'd give up in order to get a unit of y. And so we can see that if we're going in the opposite direction up the curves, we can interpret that as the inverse of the slope. And that's what we had to do to understand which of them had the comparative advantage in the y-axis variable, the graphs made. And what we could see there is that April gave up less x in order to get a unit of y than Brett did. And so she had comparative advantage in producing the y good, whereas Brett had comparative advantage in producing the x good. And that is how we understand their comparative advantage and their potential for exchange, as you will see in the next section in the book.